second colloquium of the fall semester. So today we're very happy to have, Guy comes from Brazil, and he did his PhD at Princeton University, where he worked with Juan Maldaceno, who's really one of the most preeminent, if not the preeminent theoretical physicist of our current time. And he then went, Guy then went to Cambridge University for a postdoc, and now he's a research associate affiliated with University of Amsterdam and Leiden University in the Netherlands. And he's won numerous awards, including a Fulbright Science and Technology Award and a Marie Curie Fellowship. And he's really at the forefront of this major theoretical effort that's underway now to understand what the structure of cosmological observables are and the things that we see in the CMB, the underlying theoretical conceptual structure of these patterns. And that's what he's going to tell us about today. So we're very happy to have him. Please take it away.
All right, thanks a lot, Kurt, and thanks for being here virtually. So yeah, so as Kurt said, I'm gonna talk about the distribution or the statistics of the primordial seeds of the seeds that are responsible for pretty much every cosmological observation that we see today. Okay, but before I get started, I just want to thank all my collaborators. So I'm listing them here. This is a product of work of a lot of people. These are the people that I worked most closely with. And so even if their names don't appear in the citations during the presentation, I owe a lot to them. So just a shout out to them. So I wanted to start with a statement about cosmological observations. That the cosmological observations that we make, essentially, when you look up in the sky and you're trying to study the universe at its largest scales, which is one of the main goals of cosmology, at the end of the day, what you're doing is you're measuring statistical properties of the distribution of matter and of radiation, okay? And because cosmology is famously observational, not experimental, we can't run the universe multiple times, we can just observe it, then our job is to understand the statistics of how things are distributed in the sky, and then infer what was responsible for sprinkling structure in the universe in the way we see it, okay? So that's one of the fundamental goals of cosmology, to observe these primordial correlation functions and then infer what was happening at the earliest stages of the universe that gave rise to those correlations. Before I forget, I already mentioned this to Kurt, but I encourage people to ask questions, and I understand you have a system to ask questions, but if you want to ask during the talk, or if Kurt wants to interrupt, I encourage it. You'll make it more interesting, I think, for everyone. And okay, so going back to measuring cosmological correlation functions, that's our goal, and we have multiple probes to measuring those cosmological correlation functions. The most famous one is, of course, measuring the statistics of the temperature distribution of the cosmic microwave background radiation. Now, more recently, the focus has been slowly shifting towards understanding the distribution of galaxies at the largest scales in the universe. And even more recently, we have the detection. Sorry, is there a question? Okay. Yeah, even more recently, we had a detection of gravitational waves, and now people are trying to understand if there is some stochastic background of gravitational waves, if we can measure these even in principle, what would you infer about the very early universe, and so on. And finally, one probe that we still haven't uncovered yet, but we know it's there, is to understand the 21 centimeter tracer of the so-called dark ages of the universe. So this also has the potential to have an enormous amount of information about the very early universe. So at all redshifts, we have interesting probes, and they're giving us more and more measurements of these cosmological correlation functions. Okay. So I want to start, now that I made the main statements, that our goal as cosmologists is to understand the structure of cosmological correlation functions. I just want to reveal what we know so far, and then I'll go to the new developments that have been going on in the theoretical community for the past 5 years or so. So again, when we look up in the sky, we see at the largest scales inhomogeneities. So this is a simulation of the large scale structure of the universe, like dark matter, filaments, and so on. And then you start to ask statistical questions. So the simplest question you can ask is, let me try this pointer thing. Do you see the, Kurt, do you see the?
Yep, we see it.
Okay, all right. So yeah, I have like a certain spot in the sky, and I see a certain overdensity of matter, and then I take a certain baseline in the sky, certain separation in the sky, and I ask you, if I see some overdensity there, I see a lot of matter clumped there, what's the probability that I'll see another clump of matter at a fixed separation? So then I do that, I average over the whole sky for fixed separation, and I produce a plot, okay? So this is what people call the power spectrum of density fluctuations in dark matter. Okay, and you can push this story all the way to the first light, the cosmic microwave background radiation. You can repeat this type of statistical analysis, but now for the anisotropies in the cosmic microwave background radiation. So when the universe was around 380,000 years old, give or take, after the Big Bang, then it cooled down, and then it was this hot plasma, this hot mass, and then all of a sudden, photons can start free streaming. And we see this light today, this fossil of the very early universe, and it's super homogeneous with tiny fluctuations. And these tiny fluctuations are associated to the seeds that eventually are responsible for the formation of structure in the universe. So we can repeat this statistical question of trying to correlate the distribution now of hot spots and cold spots in the cosmic microwave background. So here I'm asking the same question. I have a hot spot here, then at a fixed angular separation in the sky, what's the average value of the temperature over there? Okay, and then I can produce a plot of those things. And then our job as cosmologists is to, given these curves that experimentalists measure, to infer what was happening at the beginning of the universe. So in our standard model of cosmology, we have a few parameters. They are related to the ingredients of our primordial soup, radiation, our matter that we are made of, then so-called dark matter, and so on. But one important part of the cosmological standard model has to do with what happened at the Big Bang. So what are the primordial seeds at the Big Bang that source these inhomogeneities? Okay? So you see these beautiful plots, and if you've seen Planck data, for example, I'm sure you've seen these plots with these peaks and troughs and so on. There's beautiful physics involved in explaining those peaks. But my talk will all be about what was happening here at the beginning. So what were the seeds that were there right at the hot Big Bang? And to explain these observations, it turns out that you need very simple profile of primordial seeds. You have to sprinkle these seeds in a scale invariant fashion. In other words, you want to have essentially the same amount of power at any scale. So you have, if I have a seed of certain strength here, I have equal probability of having a seed of equal strength, like this separation, that separation, that separation. Okay, that's well, I'm sweeping something under the rug. If you actually look carefully in this line here, I'm giving it a little bit of a tilt. So it is actually, it's been detected with high significance that at short distance scales, there is a little bit less power than at long distance scales, okay? But if you have an almost scale invariant distribution of primordial seeds, then these are just like little gravitational wells, and then you have this plasma, this hot soup of the Big Bang. Then everything clumps around those primordial seeds, and then they're responsible for forming the hot and cold spots in the cosmic microwave background and the distribution of galaxies at the largest scales. But that's pretty remarkable. But it raises an immediate question, because we pull things all the way back to the Big Bang and we are seeing correlations. So I'm telling you that if I see like some strong gravitational well here, at the Big Bang, there is high probability that I see a strong gravitational well over there. So how can it be that you have correlation over distances where these points were never in contact with each other? In fact, this is it's not like a small problem, it's a big problem. If you look in the sky, this is roughly, this little circle here is roughly the size of the region that was in causal contact from the Big Bang to the moment that the cosmic microwave background radiation was emitted. So you have this super homogeneous plasma with tiny fluctuations, but from the hot Big Bang, all you could really hope for is that within this circle, you'd see roughly the same temperature. So how can it be? So this is an old puzzle that was solved. A good proposal for solving it was made in the 80s, which is the idea that actually. Sorry, question?
Do we have a question?
Oh, sorry.
Oh,
I didn't know. Sorry.
Okay. So this puzzle was a solution was put forward to this puzzle, which is the idea of cosmic inflation. Actually, cosmic inflation was so let me first define what it is, cosmic inflation. So the idea is that before the hot Big Bang, before the usual time, zero time of the standard Big Bang cosmology, people proposed, no, wait a second, there was actually a previous stage of the universe in which the universe underwent exponentially fast expansion. So this is what this curve here is showing. So then our observable universe looks so homogeneous because it was actually a tiny patch that got exponentially stretched. Okay, so it was developed to solve other problems. But then comes the beautiful fact that, you know, you can propose like some classical solution, some classical background or some smooth solution that expands exponentially fast, but you can't neglect quantum mechanics. You know, quantum mechanics has inherent fluctuations, inherent uncertainties, and the same quantum fluctuations that control atomic physics, nuclear physics, they get stretched to astronomical distances. And in fact, the symmetries, the kinematics, the dynamics of inflation works out to precisely generate these primordial seeds. So I think this is very remarkable, right? You often hear poets say, oh, you know, we come from stardust and stuff like that because of formation of heavy elements in the cores of stars, maybe science poets. But I think this is even more remarkable. So the tiny quantum fluctuations that control atomic physics, that keep the hydrogen atom from just collapsing, they get stretched to distances of the size of our universe, and they seed the formation of all the structure that we see around us today. So this is a pretty remarkable idea. Okay. So our goal for the rest of the talk is to try to explore this scenario and understand what are the implications of this scenario. So an important point that I want to make that will play like a crucial role throughout the talk is that, you know, again, we only observe these fluctuations in the sky, and with our standard cosmological model, we can push them back to the hot Big Bang. But then we just have a pattern at a fixed time, at time equals 0, the beginning of the universe. So we just have like some seeds of gravitational potential that are sprinkled at t equals 0. And then we have to say, we have to infer, or rather inflation tells us that actually there was some previous history that sourced the formation of those seeds. So we have to infer from the sprinkling of these seeds that are static at time equals 0, we have to infer some previous story, okay? And a simple way of understanding that is, you know, inflation is doing this exponential stretching. So when you look up in the sky and you're looking at very large separations, you're looking at things that were stretched for a long time during inflation. While when you look up in the sky and you're trying to correlate points that are closely separated, then they weren't stretched so long during inflation. So there is this important interplay between the time that a fluctuation took to be stretched and the distances that you're actually probing in the sky, okay? So this emergence of time will play a crucial role in the rest of the talk. So now at least we have a consistent story to tell. So we have observations and we see these primordial seeds. They seem to be there acausally, but now we say, wait a second, there was actually some previous history in which they were causally generated. You have these little fluctuations, and then they're being stretched, and that's where the correlation is coming from things that were in causal context during inflation, okay? So this is old news, but I need to recap it for the rest of the talk. One important prediction of inflation is the following. So it's a gravitational theory, right? So space-time is expanding. And I just told you that, you know, there are quantum fluctuations. So there's a little clock that is responsible for these quantum fluctuations, but space-time itself has quantum fluctuations. And so it means that, you know, we think that the space-time is expanding in a smooth fashion, but it like shears and bobs here and there. And at the end of the day, inflation predicts that actually you should see gravitational waves also. So that because this expansion is not entirely uniform. And measuring these gravitational waves is now an important goal of experimental cosmology. They leave a very particular imprint in the cosmic microwave background radiation. Okay? In particular, in the polarization patterns. So if you look with like these polarizing sunglasses, the cosmic microwave background, you should see certain swirl patterns that can only be generated from gravitational waves. And one important fact that I'm just stating, I'm not proving, but if you measure the power in gravitational waves, then you discover at what energy this phenomenon of inflation was occurring. So there needs to be some power source to make the universe expand, but we don't know what was the energy density during inflation. We don't have enough information about inflation to infer this energy scale. Okay, so that's one important goal. People are trying to measure gravitational waves, one, to confirm the inflationary scenario, two, because I think it's a fantastic prediction, right? So we see gravitational waves from black holes merging and coalescing, but these are gravitational waves of the whole universe, like contorting itself and stretching itself to get like to become smooth. Okay, and so that would be amazing discovery. And more technically, if we measure them, then we discover at what was the energy density, at what energy density this expansion was being powered. So now I'm telling you, there is this fast expansion era of the universe at some energy density that we are yet to determine. Okay. So this is all review. Okay. All that I guess has been known for a very long time, and now the rest of the talk I'm going to focus on trying to understand what happens if I try to probe correlations beyond 2 points, just point A, point B, trying to see what happens. What if I try to correlate 3 points in the sky or 4 points in the sky? What kind of physics do I infer from those correlations? Okay. So this is the main question that that drives me for the rest of the talk. So if I measure these correlation functions beyond 2 points, so at 2 points, I discovered something about the universe. I discovered that there was a certain particle that was responsible for the formation of, for sprinkling these primordial seeds. I discovered that there were gravitational waves, but can I uncover more about inflation by measuring higher point correlation functions? Okay. So now this is a relatively new development. I'm gonna move to new stuff, but maybe I can take questions. I don't know if there are any questions.
I don't see any.
Okay, so I'll carry on. So during this review part of the talk, I told you that inflation is this exponentially fast expanding area of the universe that's sprinkling the primordial seeds right at the hot Big Bang. But it's some phenomenon happening at some high energy scale. Okay, we believe actually if you try to build models of inflation, often you find out that the energy scale that your model predicts is absurdly high. Okay, perhaps billions of times higher than the energy scale of the Large Hadron Collider in Geneva. Okay, so you're getting closer to like the scale of quantum gravity than you are to the energy scales of like mundane life or even like of atomic physics. So this is an opportunity, right? Because you can ask yourself the question, can I use the early universe as some enormous particle collider? And the answer is yes. This is what we've been working on for the past 5 years or so. So it's to try to push this idea that you can think of the universe or inflation in particular as an enormous particle accelerator, and try to see, well, can we probe physics at energy scales that are probably way beyond reach of anything that we can dream of at the moment with normal particle colliders. Okay, so if I'm gonna sell you, so these pictures probably look mysterious to you. Here I'm just showing some simulation of some particle collision in the ATLAS experiment at the LHC. There are some showers and so on, and you have detectors outside, and you have to infer what was happening here at the center of the collision. And in cosmology, it's a bit of the inside out version of the story. Here we are, we observe cosmic microwave background, you observe galaxies and so on. And then we can push these things all the way back to the hot Big Bang, which is this black circle. But then the rest is really the theorist's job, is to tell what was happening during inflation that was responsible for generating these interesting correlations that we observe in the sky. Okay, and were there like some interesting new super heavy particles that you would never be able to produce in a particle collider, but you can during inflation because it's such a high energy phenomenon? So that's the idea. So I'm going to walk you through a little bit the analogy in qualitative detail. So first of all, if you're going to think of inflation as a collider, you have to ask what collides. Okay, so things that collide in particle colliders are things that are stable. You can manipulate them, you can move them from A to B, and so on. And more technical jargon, they have large 2-point functions because I can measure it here. I can measure it here, I can measure it there, and I see it like moving, it leaves an imprint in some bubble chamber or something like that. So these are stable particles. And in inflation, we have essentially two particles that we know for sure are stable because they are the ones that we actually observe their imprints indirectly later on. So these are the particles that source the fluctuations that we already see in the sky. We usually call them the inflaton, but it doesn't matter. There is some particle that's sourcing the primordial seeds that we already observe in the CMB, and the other degree of freedom that we know for sure, or the other particle that we know for sure must be there, is a gravitational particle, graviton, okay, responsible for these primordial gravitational waves. So these will be our particles that are responsible for collisions. Okay. Now, oops, sorry. Now you can ask, once you have things to collide, now you can collide them and you can ask, well, what happens when I throw them one into the other? So in a particle collider experiment, that's how I use these particles as microscopes, right? I just throw them one into the other, and then if they scatter in some interesting way, then I can infer, oh, actually at short distances, there's this interesting phenomenon going on. There's this new particle that is very heavy, very unstable, can't propagate a long distance, but is stable enough to mediate a short distance interaction. Okay, so that's how we discover new phenomena in particle colliders. And here, so the point is that we're studying scattering in colliders. So we're studying like scattering, like 2-to-2 reactions, 1-to-2 reactions, and so on. And in cosmology, then our job is to study correlations of these fellows that I just described, the temperature fluctuations and the gravitational fluctuations beyond 2 points. In particular, we're going to focus on mostly on the 4-point function in this talk. Okay, so the 2-to-2 process during inflation. So this is a typical structure of some interesting correlation function. Okay, so this black plane here is the Big Bang. Okay? So that's where I'm sprinkling the primordial seeds from which the universe starts and goes on. So now say that we, in the future, continue measuring things with better and better accuracy, and we discover some non-trivial 4-point correlation between these primordial fluctuations, okay, at the hot Big Bang. So then now the question is, what was happening during inflation that generated this non-trivial correlation? So this is a possibility of what was going on. You had some very heavy particle. Remember that inflation is this fixed energy density, like a huge energy density, like expansion thing. So I have like some heavy particle and the universe is expanding. So the heavy particle can get stretched for a little while. So this is what this is showing here. But this particle is heavy, it eventually wants to decay into lighter stuff. And then the particle decays into like some pair of the actual temperature fluctuations that we observe later on. Okay, so it's very similar to this. You see, it's very similar to this. Well, maybe I was saying words. It's very similar to this 2-to-2 process that I just described to you, right? In colliders, we throw 2 things in, observe 2 things out. But here, because we only observe the outcome, we're actually seeing some particle being produced and decaying into 2 pairs of fluctuations that are correlated in some interesting way. Okay, so we're gonna see the dynamics of this particle moving by the pattern of correlation that it leaves later on. Moreover, these particles, they are really tracing what was going on during inflation. Because you see, if I take these 4 points in the sky, and now I start to move, I have like multiple levers to play with. At 2 points, the only thing I could do really is change the arm length that I would correlate things. Now I have shapes. So I have a quadrilateral in the sky. Say I change the shape. So what am I doing as I'm changing the shape? Then what I'm doing is I'm probing physics happening during different times in inflation. Earlier in the talk, I said, when you look at long distances in the sky, you're probing things that happened early in inflation. When I look at short distances in the sky, I probe things that happen later. Okay? So if I now have a quadrilateral and I start changing the sizes of the quadrilateral, I can probe dynamics at separate times during inflation. So I should be able to see in this spatial pattern, I should be able to see the imprints of this blue particle flying in the sky during inflation. So that's what I want to show you, how it works. So to continue with this analogy with collider physics, in a particle collider, how do I discover new physics? So I increase the energy and I do many collisions, and I have some prediction of the laws of physics without a new particle, and I see like some little bumps, some deviation from one the standard model would tell me without this new particle, and I say, okay, here it is. The cross section is increasing because there's a new particle that's gluing the colliders closer to each other. Okay. In the cosmological collider, the good news is that we have this enormous energy density at our disposal. As I said, it could be, we don't know yet, but it could very well be that it's like billions of times larger than the energy scale of the LHC. But the experiment was done just once. So that's why it's hard. We have to observe many and many tracers of the initial conditions to infer what was going on. And a word about how big is the signal. So for certain theories, actually, they predict these higher points correlation functions at a level that should have been detected already. Okay. So we have already ruled out some parameter space. And actually, because of theoretical calculation, if we believe the paradigm, we have some guaranteed signal. Okay, by the way, maybe I should have said that. So here is a plot comparing the size of a higher point correlation function. For simplicity, I'm just focusing on a 3-point function. I'm just comparing the size of a 3-point correlation function to the size of the 2-point function, which we have already measured in the sky. Okay. So certain models predict big size of a 3-point function, and we could have already measured it, but it's being ruled out by experiment. So certain types of correlation functions are forbidden. So we can actually start ruling out certain models of inflation. And theory tells us that at some point we need to see something. Otherwise, inflation is just wrong. But then there is this big spanning 4 orders of magnitude window of opportunity where there could be new physics or interesting new particles. Here I call gravitational floor because at some point, in this diagram that I showed here, there is some inevitable process that you need to see because of the gravitational nature of inflation. Okay? But that's very weak because it's mediated by gravity. So we expect to see something before. But that's the goal of experiment, to go and measure it. And as theorists, our goal is to tell the experimentalists what to look for, what type of correlation you should see, where should you be looking for them. Okay. So the takeaway of this first half, that's more like first 60% of the talk, is that you can think of what sets up the initial conditions of the universe as coming from this period of inflation. And then when we trace the distribution of light and galaxies and so on in the sky, we're really seeing fossils of how these seeds were sprinkled at the Big Bang. Okay, we can use this period of inflation as some cosmological particle detector, and then our goal is to understand how to decode the imprints of interesting new particles on the statistics of these cosmological, of these primordial seeds. Okay. So now I'm going to move on to the second part of the talk, which is to try to address the question, can we find a menu of possible correlators? In other words, does anything go? Can I have any statistical distribution of these seeds, or do they have to follow some rules? Okay. So it turns out that under a mild set of assumptions, actually there is a more or less unique answer for the higher point statistics of primordial fluctuations. If you work at weak coupling, so you're assuming that these particles interact very weakly and so on. So the dominant process is essentially boils down to this process that I described early on. Okay, you have some heavy pair of particles, they get stretched and then they decay into the temperature fluctuations. Okay, but it is unique, but this unique answer has already an infinite number of possibilities, because you see, you can dial the mass of these blue particles, you can change the spin of these blue particles, you can change the coupling strength of these particles to the temperature fluctuations and so on. But the point is that it's not like anything goes. I can't just draw some distribution of seeds and measure it and go home and say it's inflation. Okay, if it came from this period of inflation, it has to come from like local causal physics. There was something happening locally here, and these particles flew in the sky in a way consistent with the laws of physics, the way we love them, and then decayed in a way that's consistent with causality and so on. Okay? And this is actually quite constraining set of requirements. So the second question is, once we know what to do, is it easy to calculate? And there is some method, or there was some method to calculate it using essentially like normal rules of quantum field theory, okay? Like some diagram technique and blah, blah, blah. But it turns out that it's actually pretty hard. It's not as simple as what graduate students learn early on in quantum field theory, Feynman diagrams. It's you can do the calculation, you can plot like on the computer some results, but we didn't have strong analytic understanding of this process, or we couldn't decode the physics behind the answer that we were getting. And then you can ask yourself, well, are there other areas of physics in which we were trying to compute something hard and actually focusing on some specific questions and demanding consistency we could do better? And the answer is yes. So there is a whole program called Bootstrap, which is a quite remarkable program. It started in the 1960s, where the goal there was to try to understand the structure of scattering of particles in colliders. The goal was to understand the theory of the strong interaction. And it was too hard to solve the strong interactions, but then people said, well, you know, if you impose certain requirements that scattering needs to happen in a way consistent with symmetry, consistent with locality, you know, with unitarity, in other words, probabilities need to add up to 1. Maybe if you focus on some small set of questions and we impose all of these constraints, you'll be able to straight up guess the answer and check that it's correct, okay? Instead of following the usual machinery of quantum field theory. And this turned out to be a super powerful method, which has been quite prominent in theoretical physics over the past like maybe 15 or 20 years. And it's found a lot of success in two areas of physics. First of all, maybe in a reduced scope, but again, the original bootstrap of the 60s maybe was too ambitious, but if you ask simpler questions of understanding the structure of scattering collider experiments, atomic coupling, and so on, there's been remarkable progress in understanding the structure of scattering. And even different type of question in understanding the structure of phase transitions in critical systems in condensed matter. So if you study critical systems in condensed matter, so say the critical points of water between liquid and vapor, there's some pretty remarkable statistical properties of this system that we really don't have good tools, or at least the simple tools of quantum field theory are not strong enough to address, to understand these systems. And it turns out that if you again ask self-consistency type of questions, you just try to ask, you know, physical principles and so on, you can pin down the answer. And this is called the conformal bootstrap. And it's an extremely remarkable program that again has been has had a renaissance over the past 10 or 15 years. So the question is, can we apply bootstrap philosophy to compute these cosmological correlators? So maybe one example is better than 1,000 words. So just to give you an example of the power of these ideas, okay? So if I want to ask the question, how do I write the, under certain assumptions of weak coupling and so on, how do I write down the scattering amplitude, in other words, the probability amplitude for two scalar particles to scatter off each other and scatter into two other particles as a function of the data of these particles, as a function of the momenta of these particles? Then it turns out that if you just ask that the answer is compatible with the symmetry, with locality, and with unitarity, you can just write down the full answer. That's it. So I just want that to sink in because it's such a powerful statement. If you're used to quantum field theory, it's probably wired into your brain. But if you take a step back and think about it, it's a really powerful statement. So if you look at scattering amplitude, a 2-to-2 scattering amplitude, to begin with, you need to specify 12 pieces of data because you need to say in direction X, Y, and Z, the velocity of each particle. You have 4 particles, 3 directions, you have 12 pieces of data. And just from symmetry alone, I claim that in the end, the only 2 degrees of you only have 2 degrees of freedom. So you go from 12-dimensional space. So you imagine, oh, how the hell am I gonna write a function of 12 variables? But symmetry buys you, actually it's a function of 2 variables. But now, so okay, so this is what symmetry buys you. Now locality buys you that you get this very simple structure like polynomials and like, you know, functions. This is just some polynomial, some Legendre polynomial. It's not important. And maybe a slightly more complicated thing, some rational function. You have some denominator. Okay? But even the structure of the denominator is dictated by locality. So for example, you can't have a denominator with this variable s squared. So that's forbidden. Locality forbids you from doing that. And finally, there's even a little bit of unitarity wired in here. You see there's some g squared here. So this g squared is some positive number, and it has to do with the fact that once I massage this expression onto some probability of particles colliding into other particles, probabilities must be positive. So the avatar of probabilities being positive is related to this g squared. Okay? So that's it. So all the freedom you really have is in this mediator particle having certain properties. And symmetry again tells me that all particles in the universe are labeled by two pieces of data, mass and spin. Okay? So given the mass, given the spin, mass is here, spin is here, that's it. Okay? So you solved an infinite number of problems with just a couple of rules. So the question is, can we apply this to cosmology? And that's the figure that you saw on the flyer. We call the Cosmological Bootstrap. So we're going to try to infer from these patterns in the sky physics that was consistent with symmetry, that was consistent with locality, and that was consistent with unitarity. And we'll see that once we impose all of these requirements, then in a way, it's technically more complicated, but physically, you'll be precisely analogous to the formula that I just showed you. And then we'll be done. We classified the menu of inflationary correlators that are compatible with the rules of physics. And then we can go and try to measure them and infer, was there a particle, certain mass, certain spin that was active during inflation. So this gets a little bit technical, so I'll just flash some highlights. So first of all, inflation in its simplest incarnation is as symmetrical as our standard flat space. So this is what's called DS, de Sitter space. So again, remember I said we went from 12 pieces of data to 2 pieces of data. So we used 10 symmetries to reduce the number of possibilities. And in the Sitter space, again, you have 10 symmetries at your disposal to collapse 2 to 2, scattering, to depend only on 2 pieces of data, okay? And here's the remarkable thing. Actually, we only observe, again, so this is inflation, right? So this is the expanding universe. This is the Big Bang. And actually, we only understand the universe after the Big Bang, and we have to infer what was happening during inflation. So really, all we have access is this surface here, this hot Big Bang surface. Now you can ask yourself the question, how do the symmetries of inflation reflect themselves on this fixed surface? And it turns out that it's exactly the same symmetries that control the water vapor phase transition. So the physics of boiling water is the same physics, at least at the level of symmetries, of the primordial seeds of our universe. Okay. So that's it. So this is the setup. So we have a lot of symmetry at our disposal. So let me just create some intuition about the kinematics. I'm trying to determine this 4-point function in the sky, and I want to infer the shape or the correlation, how much power there is as I move the points in the sky. How is the amount of power that I see reflecting the physics of what was going on during inflation? So here's something that is gonna be shown to you in a second, that you see how remarkable these shapes are. So you see, let's say we start with all 4 arms with roughly the same length. Say I start with a square or something like that, okay? So recall from the beginning of the talk, if I look at a fixed separation in the sky at a certain distance, I'm probing a given time during inflation. So if all the arms of the quadrilateral have roughly the same size, I'm roughly probing physics at the same time during inflation. So then I'm roughly probing very short range correlations during inflation. So almost contact-like interactions. Okay. Now I start changing the arm lengths. Okay. So I make these arm lengths here a little bit bigger than these 2 other arms. So now I must be probing, I'm probing larger and larger scales, I'm probing earlier and earlier times. So then I should really see, as I dial these points in the sky, I should really see the imprints left from these new heavy states moving throughout inflation. So I should see time evolution in the spatial pattern. So I'll show you how it works. Okay. So maybe I'll skip this and just show you the answer. So again, if I start from some quadrilateral, like some square in the sky. I'm probing physics at a given instant in time, and I see like some boring shape, some certain amount of power. The power is biggest when it's a square, and then as I start collapsing the square, this particle is going to start. I'm going to see some particle flying in the sky. So the amount of power starts shrinking. Okay, so this is in this plot here. This is like I blew up the picture to emphasize the feature, but here power is the biggest around here, around the quadrilateral shape. So again, I start from a square in the sky, then I see a big amount of power because I'm correlating things at short distances during inflation. And now as I collapse the quadrilateral, say I make the diagonal very small, then I'm essentially giving a lot of time for this new particle that I can't observe directly to fly during inflation. And you know what? I see some pattern. So as I squeeze the quadrilateral, the amount of power I see in the sky should go up and down. And what I'm really seeing, even though I'm just dialing some pattern in the sky, what I'm really seeing, these oscillations, are just the phase from quantum evolution of this particle. This particle is a wave. It's like moving throughout inflation, and it's picking up a phase as it moves through the sky. So these oscillations are really the imprint of the quantum oscillations of these new states during inflation. So I think that's super beautiful. Right? You're seeing in a spatial pattern in the sky, time evolution of this heavy particle. Actually, I just want to flash this equation to you because it shows cleanly time evolution from spatial patterns. So it turns out that if you actually go to the equation that you have to solve and so on, if you change variables, so these U and V are related to the arm lengths of these 4 points in the sky. Okay, recall this is the hot Big Bang surface, and then this is inflation. Time goes up. So if I change variables from these arm lengths, these U and V arm lengths, to some new variable that I call T, then the equation I have to solve in a certain limit is this. And then you should recognize this equation immediately. Is the equation of a harmonic oscillator with some forcing term. So the equation of harmonic oscillator is just the fact that you have some particle moving in the sky, and the forcing term is coming from the expansion. So you have this powerful particle collider. It's giving you some forcing term. It's pulling things apart, and this is the forcing term. And then as I pull things apart, my particle needs to move in the sky, and it oscillates. And you're seeing in the spatial patterns the time evolution equation of this new particle. Okay. And this is just a technical remark. This makes life so much simpler. So in the early days of computing these shapes of statistics of correlation functions, of computing correlation functions of primordial fluctuations, you would write a paper for for every different process. You would write a paper following like some complicated recipe and so on to get the answer. And now, if we understand this process for a massive particle, the slide that I just showed you that plots, then just from kinematics, again, the power of symmetry, I can just apply some simple operations, basically a bunch of like derivatives and multiplying by stuff and so on. I can get from the single diagram, I can reproduce what was known in the literature. But now we know much more. We know the answer for any mass, any spin. Essentially, we know the full menu. Okay, so this is the power of the symmetry argument. So the takeaway this cosmological bootstrap philosophy is that even though you have infinite number of choices in principle at your disposal, because you can have, you know, mass and spin and so on of this intermediate particle, the shape is not arbitrary. In fact, it's highly constrained and essentially uniquely determined by imposing that the answer is local, unitary, and follow the symmetries. In fact, what we do is we just anchor ourselves to this Big Bang surface, to this end of inflation surface, and just ask a question there, and then infer from the answer of this question consistent time evolution. We didn't time evolve things. We just asked a question at the end of inflation and got an answer that was consistent with time evolution. Okay. And now in the last, do I have 5 minutes, Kurt?
Yeah, you have 5 minutes.
Okay. Yeah, the last 5 minutes, I just want to flash. I think that I hope I convinced you that this is a powerful method to understand the statistics of primordial fluctuations, but maybe ultimately is the way to understand fundamental physics, actually what gave rise to inflation, for more both conceptual and technical reasons coming from quantum gravity. Okay. So this cosmological bootstrap is connected to various areas of theoretical physics. Mostly I focus on observational cosmology and inflation, okay? But I just want to highlight an important thing. I made this connection to collider experiments, and in particular to scattering. And I showed it as a cartoon early in the talk, but then I gave you this example from the bootstrap and said, okay, there's a very analogous story that happens in the case of cosmology. But actually what I didn't tell you is that there is a particular limit. There is like a certain mathematical limit. It's not physical. You can't observe it in the sky. But if I hand you the formula for the cosmological correlator, you can take a certain limit where you zoom in into short distances into the cosmological correlator, and you measure, and what you see when you zoom in is you see a scattering process. So actually, it turns out that cosmological correlators are an enlarged version of a scattering amplitude. So they must encode all the beauty that people have been seeing in the development of scattering amplitudes. So I'm just flashing some words. There have been all sorts of interesting developments. And now we're just starting to learn how these things appear in cosmology. So there are all of these fancy, interesting techniques that shed a lot of light in the structure of scattering. And because I told you there's a certain limit of the cosmological correlator that gives you scattering, then it begs the question, is there a cosmological version of all of these beautiful things that people have discovered over the past 15 years? And we don't know, but there's already a lot of people working on it, and we're starting to see that the simplest, at least some of the simplest things that you see in scattering do have cosmological analog. And we actually expect that all of these structures should have cosmological analogs, because cosmological correlator contains the scattering amplitude. And one of the goals of this program is to actually start to carve the space of possibilities, just to tell an experimentalist, look, you should see this pattern with this and that type of correlation, maybe this of that size, because if you see something different, it's inconsistent with the rules of physics the way we know and love them. And finally, I want to touch on this connection with holography, which is where I'm going to finish the talk. So we've seen over the past 20 years that if you want to add gravity to questions in quantum physics, it's always helpful, maybe essential, to pin yourself to some boundary where gravity switches off, and you can anchor yourself in some platform and ask certain questions and infer the dynamics of quantum gravity from there. And this is its most remarkable circumstances happens in space-time, they are completely different from ours. They are more like potential wells, so-called anti-de Sitter spaces. And in flat space, we do have some avatars of this type of questions where you just anchor yourself to the boundary here at the end of space-time and ask a question, and then you infer what was happening here in the middle when quantum gravity effects are taking place. And this question is the most pressing in the case of what was happening at the actual Big Bang. So, inflation started, but we don't know what was happening at the beginning of inflation. We haven't solved the beginning of the universe question. And maybe if we take these lessons from quantum gravity seriously, then we should anchor ourselves to some platform. And the natural platform to anchor ourselves on is this surface, the hot Big Bang surface, which is the end of inflation, and try to ask certain questions and ask certain consistency requirements of these correlators. And if we are clever enough, we should be able to infer what was really happening at the Big Bang. Okay, so eventually the ultimate goal is to just forget about this picture of time evolution. Just have like a certain question that you ask at this hot Big Bang surface. Just you see this pattern of seeds and you say, if it came from consistent time evolution, these seeds must have satisfied this and that property. We don't know what these properties are. Okay, but that's the ultimate goal. And if we understand those questions, then ultimately we might be able to actually tell what was happening here. So the final takeaway, I hope I convinced you that the statistics of primordial seeds, or the initial conditions of the universe, they are this important theoretical laboratory where we can test our ideas of fundamental physics, where quantum mechanics and general relativity play a role together. Tiny quantum fluctuations get stretched. And to understand the statistics of the fluctuations, we do need to use tools from other areas of physics, condensed matter physics, particle physics. And these tools are shedding new light on the structure of cosmological correlations and are telling us that we should be asking questions, really anchor ourselves at this hot Big Bang surface. And ultimately, that's great. It gives us calculational power, but it might be ultimately necessary if we want to understand what happened at the Big Bang. So that's it. I'll take questions now. Thank you very much.
All right, thank you. So for questions, if you have questions, you can raise your hand and ask, or you can type it in the chat. Let's see, so Harsh has a question.
Yeah, I'm already unmuted, so I can speak.
Okay.
That was a very beautiful result that you described for the cosmological correlators using the bootstrap. But I was wondering how reliant it is on the space-time being exactly de Sitter, and whether there might not be significant corrections that one might actually see in the real universe.
Yes. Yeah, it's a great question. So I can say a couple of things about it. So first of all, even in these original bootstrap calculations, we can deform a little bit away from de Sitter. So we can, for example, study slow roll, so-called slow roll models of inflation, in which the universe has tiny deviations from de Sitter, and we can adapt the cosmological bootstrap to those setups. But actually we just finished, I just organized a workshop this week, and now people are applying these bootstrap rules, and they can, for certain specific, not for these massive particle exchange type of diagrams, but for some simpler processes, people now understand the rules even when the deviations from de Sitter are strong. So maybe I should mention to the audience, there is an important interplay between breaking the Sitter symmetry and having a large signal. So usually when you deviate significantly from the Sitter, meaning that the background is still almost the Sitter, but the way particles interact it's not respecting the symmetries it's breaking the symmetries in a relatively strong way, you tend to have a larger signal. So that's phenomenologically very interesting. And now people understood how to adapt bootstrap rules for certain simpler types of correlators, not the ones I described here, but this is a brand new development. So I do expect that very soon we'll be able to apply the bootstrap philosophy even for cases in which there is large breaking of the Sitter symmetry.
So one question I had was whether you really, so you talked about this weak coupling in de Sitter space to be able to draw pictures of particles colliding and so on. But in the conformal bootstrap, we don't really care about whether it's weakly coupled or strongly coupled. Can you say something about whether there are strongly coupled possibilities for an inflation and how this?
Yeah, I think in principle there are, but then we don't have any calculational control. So we do need to find the rules of the conformal bootstrap of cosmology at strong coupling. And our hope is that if we understand these simple processes, we'll be able to infer the rules of the cosmological bootstrap that will apply at any value of the coupling constants. If you a little bit more technically, we're solving the conformal bootstrap in the so-called large N limit, which is corresponding to weakly coupled bulk dynamics. But the hope is that if we understand these processes well enough and we gather enough theoretical data, we'll be able to abstract the rules and explore these possibilities in which the inflationary dynamics was more strongly coupled.
Okay, I'm wondering if do you know, Harsh, are you able to raise, people able to raise their hands who are not hosts?
I think I should be able to.
I'm a little worried that that's just not working.
Yeah, no, there's a question now in the chat from James.
Okay, yeah. So James asks, is the hope that there's some analog of the crossing equations?
Yes, I think that's the hope, but technically it works. It's certainly what we know for sure is that it works differently than it works in condensed matter systems. But yeah, but the hope is that such equations do exist. We know a little bit about how to adapt the rules, but we don't know enough yet to either rule out crossing equations or confirm their existence.
Okay, and we had a question from Glenn, who should now be able to talk.
Hey, Guilherme, thanks for the beautiful talk. I was wondering, what are the prospects for making the measurements of these correlators
yes,
sensitive enough that you could probe these interesting conclusions?
Yeah, actually, I'm currently investigating this because you can ask, wow, in the cosmic microwave background, if I keep measuring things with more and more accuracy, how much better can I do? And the answer depends very much on the details of these, the particular details of the shape. So there are, yeah, so I can say a couple of things. So first of all, these features, I expect that they will buy you some power. So even if you have limited information, because they are features, you might have a better chance of measuring them. But I don't know yet. I can't give you a precise number of how well we'll be able to do. But what I can tell you that I think is interesting is that if I have this 4-point correlation function, and then this intermediating particle is light, it doesn't leave these wiggles. It's more like a ultra damped oscillator. So it's more like it leaves a long tail as it decays. Then depending on how slowly it decays, then I think we have some hope of measuring just from brute force mode counting arguments, just from seeing, you know, the future surveys will do better by certain factor in the number of modes. And I think we'll be able to get stronger constraints. Okay, so that's one thing. From a model builder perspective, I think you can crank up the size of these correlation functions to be on the verge of detection. Okay? But you see, there's an important interplay here. So the first thing you should see is the smooth, boring signal, in technical words, equilateral non-Gaussianity. And then as you, maybe I should draw a picture here. So you should see power. I was mostly talking about quadrilaterals. It applies to triangles, everything I'm going to say, but I was talking about quadrilaterals, so I'll stick to quadrilaterals. So the signal is really the strongest here, but the feature is the strongest here. So for those massive particles that leave these oscillations, I think you need to see this first. And then you have the strong prior that you've seen something here, then you go hunt for a feature. But now, if the particle is very light and leaves a strong tail instead of these oscillations, then what I'm finding is actually that here you might have a better hope. And it has to do with damping, with the fact that the CMB surface actually has some blurriness. I can tell you technically how it works if you want later, but yeah, it's work in progress. We're trying to investigate it.
Okay, so from Edith, would we be able to distinguish the primordial features from nonlinear features in galaxy surveys?
Yeah, it's an excellent question. And I don't think there's a theory yet, but the philosophy is that if you look at, so the features are imprinted at the largest possible scales, okay? So the idea is that the universe is not old enough at the moment that you're doing galaxy surveys for these features to have been washed out by nonlinearity. So that at least we're lucky. So the signal tends to be weaker where the features appear, but at least the features appear at the largest scales. So we do not expect the features to be washed out or by nonlinearities. But there, as I said, there's no theory of this yet. It will be very interesting to develop a theory proving that certain features that you imprint in the early universe cannot be washed out later on. There's something for the BAO feature, right, the baryon acoustic oscillation features, but for this type of primordial features, there's only this intuition.
And she adds, if we don't find any, what fundamental insights would we get about inflation? Let's see, I should just unmute Edith here. How do we? Okay, I think Edith, you should be able to talk.
Yeah, thanks. Yeah.
Hi.
Hi. Yeah, I guess I'm just curious, so I tapped it, if we end up not finding any, say there really isn't any primordial non-Gaussianity, I guess, in the early universe, then, or 4-point functions, and what would we, so this should say something very fundamental about inflation.
Yeah, I think there is, okay, so there is, there's some, what we call gravitational floor, where if we really, to get there, you need to go futuristic. You have to go to the dark side of the moon, probably, with some 21 centimeter survey there. But okay, there are enough modes in the universe to go that far. And from the measurements of the 2-point function, if we believe in inflation, when we get to that point, we should see something, which was this diagram which is this diagram here, the exchange diagram, when you exchange the graviton itself. So just gravitational nonlinearity during inflation, not the gravitational nonlinearity that was asked later on, right? Maybe by yourself. So, so there, if it was a gravitational theory, we should see this signal. But because it's graviton mediated, it's like very small, it's Planck suppressed and so on. But if we don't see anything there, then probably it's just not inflation. And we need to go back to the drawing board. So that's one thing I can say.
Okay, I don't see any further questions, so I think we should wrap up and thank Guy again. And we'll reconvene next week at the same time. And Harsh, do we do the